On June 23, 2025, in a public event held in Washington, D.C., a group of scientists pulled up a single image on a giant screen, and for a moment, the room went completely silent. It wasn't a photograph of one galaxy, or even a handful of galaxies. It was millions of them, captured in a single frame, alongside thousands of previously undiscovered asteroids that nobody on Earth had ever seen before that exact morning. Planetariums around the world had organized watch parties just to witness the unveiling live. Astronomers who had spent their entire careers studying the universe one small piece at a time were looking at something that made all of that work suddenly feel like it was about to move at a completely different speed. This is the real story of the Vera C. Rubin Observatory's first images, what was actually inside them, why they mattered enough to stop rooms full of professional astronomers in their tracks, and what's happened since that first unveiling as the observatory has moved from a single stunning debut into the start of an actual 10-year mission. If you want more real science, explained without the exaggeration, subscribe now, because this story is still unfolding. To understand why this particular debut generated the reaction it did, you first have to understand what this telescope actually is, because it isn't just another large telescope added to the growing list of major observatories around the world. The Vera C. Rubin Observatory sits on a mountain called Cerro Pachon in northern Chile, in the foothills of the Andes, a location chosen specifically because its high altitude and extremely dry air provide some of the clearest, most stable skies for astronomical observation found anywhere on the planet. It's jointly funded and operated by the U.S. National Science Foundation and the Department of Energy's Office of Science, the result of roughly 2 decades of planning, engineering, and construction. At its heart sits the largest digital camera ever built for astronomy, feeding data from an 8.4-meter telescope specifically engineered to do something most major telescopes were never designed to do: move quickly and photograph enormous swaths of sky, repeatedly, night after night, for an entire decade. That mission has an official name, the Legacy Survey of Space and Time, and its goal is almost difficult to say out loud without it sounding exaggerated, except that it isn't. Over the next 10 years, Rubin is going to systematically scan the entire visible southern sky roughly every few nights, building what the observatory's own team has described as the greatest cosmic movie ever made. A continuous, ultra-high-definition record of the universe capturing literally anything that moves, flickers, explodes, or changes brightness across the entire sky, essentially in real time. But before any of that 10-year survey work could officially begin, the team needed to prove the entire system actually worked. Cameras, mirrors, software, and data pipeline together as a single functioning instrument. That's what the June 2025 unveiling actually represented. The first real proof, shown publicly, that this telescope could do exactly what it had been built to do. It helps to understand just how much engineering had to come together to make images like these possible in the first place. Because building a telescope capable of moving this fast, while still capturing this much detail, required solving problems that had never been fully solved together at this scale before. The camera at the heart of Rubin, built primarily at the Department of Energy's SLAC National Accelerator Laboratory, is roughly the size of a small car, and its focal plane is large enough that a single one of its full-resolution images would require hundreds of ultra-high-definition television screens arranged together just to display in full. The telescope itself uses an unusual 3-mirror design, allowing it to capture an extremely wide field of view in a single exposure while still keeping image quality sharp all the way to the corners of the frame. A combination that's genuinely difficult to achieve, since wide fields of view and corner-to-corner sharpness tend to work against each other in more traditional telescope designs. Every night Rubin operates at full capacity. It's expected to generate roughly 20 terabytes of raw data, all of which has to be processed, compared against previous images of the same patch of sky, and checked for anything that changed within about a minute, so that alerts about new asteroids, supernovae, or flaring black holes can reach astronomers around the world, while those events are still actively unfolding. The images themselves, gathered using just over 10 hours of test observations, were staggering by any reasonable standard. One image, which the observatory nicknamed the Cosmic Treasure Chest, captured a section of the Virgo cluster roughly 55 million light-years from Earth, containing an estimated 10 million galaxies within a single frame, itself representing only a tiny fraction of a percent of the total galaxies Rubin expects to observe across its complete mission. A second image, built by carefully stacking 678 separate exposures gathered over just over 7 hours of observing time, revealed the Trifid and Lagoon nebulae in extraordinary new detail, showing delicate structures within their surrounding clouds of gas and dust that simply hadn't been visible with this level of clarity before. And a third image, nicknamed the Ocean of Stars, showcased the constellation Lupus using a full 7 gigapixel frame, showing off a level of resolution and color depth that left even seasoned observers in the room audibly reacting as it appeared on screen. If a story built on real, verified data, straight from the scientists actually running this telescope, is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. It's worth comparing this moment to a similar debut from decades earlier, because Rubin isn't the first telescope whose first images genuinely reshaped how astronomers thought about their own field. When the Hubble Space Telescope finally began producing clear, corrected imagery in the early 1990s, after its now famous initial optics problem was fixed in orbit, its early deep field images, staring at a single, seemingly empty patch of sky for an extended period, revealed thousands of previously unknown galaxies packed into a region that had looked completely dark to every previous telescope. That single image fundamentally changed how astronomers understood the sheer density of galaxies filling the observable universe, and it remains one of the most referenced results in the history of the field more than 3 decades later. Rubin's debut represents something related but distinct, not a single unusually deep stare at one tiny patch of sky, but proof that an entirely new kind of telescope can repeat something like that result across the entire visible sky every few nights for 10 consecutive years. If Hubble's deep field showed astronomers how much more universe was out there than anyone previously realized, Rubin's first images demonstrated that an instrument now exists capable of actually surveying all of it repeatedly, rather than requiring years of dedicated observing time pointed at one single, carefully chosen spot. It wasn't only galaxies and a nebulae that made this debut so remarkable, though. During that same brief 10-hour test period, Rubin's cameras identified thousands of previously unknown asteroids moving through our own solar system, a discovery rate so far beyond anything achieved through traditional survey methods that it genuinely startled researchers who track near-Earth objects for a living. The observatory's own scientists have since stated plainly that Rubin alone is expected to discover millions of new asteroids within just the first 2 years of its full survey, and that it's expected to become the single most effective observatory ever built for catching rare interstellar visitors, objects passing through our solar system from other star systems entirely, often spotting them earlier in their approach than any previous telescope has managed. Beyond the still images themselves, Rubin's very first dataset also captured something that photographs alone can't fully convey: actual change happening in the sky over time. Among the very first scientific results pulled from that initial test data, researchers identified 46 separate pulsating variable stars, stars that regularly brighten and dim in specific, measurable patterns that reveal detailed information about their internal structure and behavior. Finding that many variable stars in such a small slice of test data was itself a meaningful early signal of exactly how well suited this telescope is for its actual scientific mission, tracking change across the sky continuously rather than capturing a single static snapshot, the way most telescope images have traditionally worked. If you found these numbers as staggering as I did while researching this, drop a comment letting me know. It genuinely helps me figure out what to cover next. Part of why this specific unveiling generated such a strong public reaction beyond the scientific community itself came down to how deliberately the observatory's team built the announcement to be genuinely experienced, rather than simply reported on. Planetariums across the world, including major institutions like Chicago's Adler Planetarium, hosted live global watch parties specifically timed around the Washington unveiling, allowing the public to experience the reveal collectively rather than simply reading about it afterward. Rubin's team also released an interactive sonification tool through something called the Sky Viewer app, translating the colors, brightness, and structure of the observatory's ultra-detailed cosmic imagery into an actual, immersive soundscape, letting people effectively listen to a piece of the universe rather than only look at it. Planetariums have since incorporated the imagery into full dome shows, giving audiences an experience considerably closer to actually floating through the data Rubin captured than a traditional flat photograph could ever provide. There's something worth appreciating about the specific decision to build a sonification experience alongside the raw imagery, because it reflects a deliberate choice by Rubin's team to make this data accessible beyond just professional astronomers reading numbers off a chart. Translating brightness, color, and structure directly into sound gives people without any background in astrophysics a genuinely intuitive way to experience the scale and texture of what the telescope is actually capturing, drifting through a soundscape built entirely from real observational data, rather than a purely artistic reinterpretation of it. Combined with the full-dome planetarium presentations built around the same imagery, the overall approach reflects a broader recognition among the people running this project, that a 10-year survey producing this much data has value not just as a scientific resource, but as something the public can genuinely engage with directly, rather than only reading about secondhand once a research paper eventually gets published. Officials involved with the project were direct about what this moment actually represented for American science more broadly. Michael Kratsios, director of the White House Office of Science and Technology Policy, described the observatory at the time of the unveiling as an investment in the future, one that would lay down what he called a cornerstone of knowledge for future generations to build on. Patrick McCarthy, director of NSF's Noir Lab, described the unveiling of Rubin's first images as marking the beginning of an entirely new era in astrophysics. And the observatory's own team, in the materials released alongside the imagery, put it simply, describing Rubin as bringing the universe to life, illuminating what they called a treasure trove of discoveries, pulsating stars, supernova explosions, the fossil record of ancient galaxies, an entirely new phenomena that had never been observed before at all. It's worth spelling out exactly how a telescope, taking pretty pictures, actually helps solve something as abstract as the nature of dark matter, because the connection isn't obvious at first glance. Massive objects in the universe, galaxies and clusters of galaxies, bend the path of light passing near them due to their gravity, an effect called gravitational lensing, subtly distorting the apparent shape of more distant galaxies sitting behind them from Earth's point of view. By measuring that distortion across enormous numbers of galaxies spread throughout the sky, and tracking how that pattern of distortion changes as Rubin repeatedly images the same regions over the coming decade, researchers can build an actual statistical map of where invisible matter is concentrated throughout the universe, based entirely on its gravitational fingerprint, rather than any direct detection of the material itself. Doing that kind of measurement reliably requires an enormous number of galaxies observed with extremely consistent image quality across the entire survey area. Exactly the kind of data set a single telescope repeatedly scanning the whole visible sky for 10 years is uniquely positioned to produce, in a way that combining data from many smaller, less consistent surveys never could quite match. That first debut wasn't the finish line, though. It was explicitly framed by the team as a preview, a proof that the instrument worked exactly as designed, ahead of the real 10-year mission still to come. And a full year later, that mission actually began. On June 30th, 2026, following months of additional testing, calibration, and a formal operational readiness review, Rubin Observatory officially started full science operations for its actual legacy survey of space and time. Brian Stone, currently performing the duties of the vacant National Science Foundation Director role, marked the occasion directly, stating that the observatory was now beginning to film what he called the greatest cosmic movie ever made, and describing the moment as reflecting decades of vision, innovation, and the power of sustained federal investment in fundamental science. By the time that full survey officially began, Rubin had already proven its scientific value well beyond that original debut. Using engineering and optimization data gathered in the months leading up to full operations, the observatory had already detected more than 11,000 new asteroids and logged dozens of additional newly identified objects throughout our own solar system, all before its formal 10-year mission had technically started at all. According to the observatory's own release marking the milestone, the color-rich images Rubin continues to produce of exploding stars, active black holes, and cosmic collisions are also expected to help direct the attention of other observatories around the world, allowing multiple institutions to work in tandem, observing the same notable celestial events from different angles and instruments simultaneously, something that would be considerably harder to coordinate without Rubin's continuous, wide-field monitoring flagging exactly where and when something interesting is actively happening. There's a practical significance to that asteroid hunting capability that goes beyond simple scientific curiosity, too, one worth taking seriously in its own right. Every new asteroid Rubin identifies gets checked against known orbital paths to confirm it poses no risk to Earth, a routine but genuinely important part of planetary defense that benefits enormously from a telescope capable of finding this many previously uncatalogued objects this quickly. The overwhelming majority of asteroids discovered this way turn out to be harmless, distant objects with no realistic chance of ever coming close to our planet. But the entire practice of planetary defense depends on actually finding and tracking these objects in the first place. Since an asteroid nobody has ever detected can't be monitored, modeled, or prepared for at all, Rubin's ability to catalog such an enormous number of new objects so quickly represents a meaningful step forward in humanity's overall capacity to maintain a complete, current map of everything moving through our own solar system, quietly reducing the odds that something genuinely hazardous could ever catch scientists by surprise. It's worth pausing on the name behind this observatory, too, because it wasn't chosen arbitrarily. Rubin honors Vera Rubin, an American astronomer whose research in the 20th century provided some of the most compelling evidence ever gathered for the existence of dark matter, the mysterious, invisible material that appears to make up a substantial portion of the universe's total mass, detected only indirectly through its gravitational effects on the stars and galaxies we can actually see. Understanding dark matter, along with its equally mysterious counterpart dark energy, the force that appears to be accelerating the expansion of the universe itself, sits at the very center of what this observatory's entire 10-year mission is actually built to help resolve, studying how the light of distant galaxies gets subtly distorted by the gravity of the invisible matter surrounding them across a scale and volume of data no previous survey has ever come close to matching. So, what does all of this actually add up to? In a little over 10 hours of test observations, a brand new telescope produced images so immediately striking that they stopped a room full of professional astronomers into silence, images containing millions of galaxies, thousands of newly discovered asteroids, and dozens of pulsating stars never before cataloged, all captured before its real mission had even officially begun. A year later, that same observatory formally started the actual 10-year survey it was built for, already carrying a track record of more than 11,000 confirmed new discoveries gathered during nothing more than its own preparation and testing phase. What makes this particular story worth returning to over the coming years is that almost everything covered here still technically counts as the opening act. Rubin's own team has been consistently clear that the debut imagery, however striking, and the asteroid totals gathered during commissioning, however record-breaking, represent only the very beginning of what a full decade of continuous, wide-field observation is actually capable of producing. The detailed maps of dark matter's distribution across the observable universe, the precise measurements of how quickly cosmic expansion is accelerating, the complete, multi-year record of billions of galaxies changing brightness and structure over time, all of that is still ahead, building up gradually with every single pass Rubin makes across the same patches of sky in the years still to come. If stories like this, grounded entirely in verified data straight from the scientists and officials actually involved, are what you come here for, subscribe to this channel and turn on notifications. Because Rubin's real 10-year survey has only just begun, and there's a very real chance the results still to come make this opening chapter look modest by comparison. Thanks for watching, and I'll see you in the next one.